So I'll be speaking about this paper, which is joint work with Alexey Gorshkov at the University of Maryland and Bill Fefferman at the University of Chicago. And let me begin with the motivation behind this work. So the problem of studying ground states of various interesting systems is an important one across the sciences. For example, in condensed matter physics, in quantum chemistry, even high energy physics, and in the seemingly unrelated topic of optimization in computer science. So given the importance of this problem, and so this is exactly a problem that we would like to solve, let's say using quantum algorithms. And because this is such an important problem, you can ask the question of how feasible this is for general Hamiltonians. And so we can answer this question from two sides. One is complexity theory, which tells us when the problem can be hard. And the other is from the point of view of algorithms, which tells us when the problem is easy. And these two branches of effort often support, inform, and complement each other. So from the point of view of complexity theory, a field of study known as Hamiltonian complexity has emerged over the last 2 decades or so, which aims to study precisely this task of studying ground state properties. So the prototypical problem in this field is the local Hamiltonian problem, in which we are given, say, a description of some n-qubit Hamiltonian, H, which is a sum of local terms, Hi. And by local, I mean that each term acts on at most k qubits. And so this is called k-local. And we are asked to estimate the ground state energy of this Hamiltonian H. So Kitai's result was that it is QMA hard to solve this problem if you're interested in inverse polynomial additive error, where n is the number of, say, qubits the Hamiltonian is supported on. So note that QMA is a quantum generalization of NP, which means that it's very unlikely that quantum computers could solve this problem in general. So more recently, the problem has been studied with respect to inverse-exponential additive error, which is a bit more stringent, and that's shown to be PSPACE hard. And the motivation for this is will be clearer later in the talk. But for now, I'm going to be calling this regime of inverse-exponential additive error, which is like a really high precision regime, calling that the precise regime. Okay, so from the other point of view, on the algorithm side, we do know efficient algorithms for some special cases. For example, when you have 1D Hamiltonians plus a spectral gap, this problem is known to be in P. Similarly, we also have quantum algorithms that can sometimes take advantage of certain specific features in the problem, such as if you have a state with high overlap with the ground state. So check out this talk by Lin and Tong on Friday. And furthermore, because of the importance of this problem for quantum chemistry, several heuristic algorithms have been developed, most notably the variational quantum eigensolver. And so, yeah, given all these facts, we can ask, how do these results fit in with QMA hardness of the problem? And as I said before, easiness and hardness are different but complementary routes of understanding the landscape of the problem. And one should try to bridge the two as far as possible. So the QMA hardness result that I mentioned on the previous, like the last 2 slides, is a bit too general to be useful, because all it says is that there are like worst case instances of k-local Hamiltonians that can be really complicated. But this has been rectified to some extent by giving hardness results for Hamiltonians, even with very reasonable restrictions on how the Hamiltonian should look like. such as spatial locality. So you can put the spins, so we show this for qubits in 1 dimension or qubits in 2 dimensions. We can also impose restrictions like translation invariance and also restrict to specific terms in the Hamiltonian and so on. So what we'd like to do is identify some structural property that voids these generic hardness results, and that can also be exploited by algorithms. So in this talk, we'll consider 2 ways of adding structure to the problem. So the first of these is the spectral gap, which is a very important quantity in physics and is often associated with really nice properties such as the existence of tensor networks and ground state area loss, which is rigorously proven in 1D. There's also several senses in which the existence of a spectral gap implies tractability, such as in the adiabatic algorithm, the minimum spectral gap from the initial Hamiltonian to the final Hamiltonian is what determines the runtime of the algorithm. Also, as we have seen before, in 1D, when you have a gap, when you have a spectral gap, it implies an efficient computation of ground state energies. On the hardness side, however, I would say that we do not know so well the status of the spectral gap. In particular, we know that hardness results are, we don't know if hardness results can be made to survive, even if the spectral gap is vanishing in the system size. So if it vanishes inverse polynomial in the system size. And that's because the clock construction, which is one of the often used techniques for showing QMA hardness, is not super malleable. And our work fits into this whole scheme by giving some initial piece of evidence that the spectral gap makes the problem easier in general. And this brings us to our first main result, which is that there's a provable setting where the spectral gap affects the complexity. So informally, we want to compute the ground state energy of some Hamiltonian whose gap is at least delta to inverse exponential precision. And because we are talking about inverse exponential precision, this problem is much harder than QMA. And as we have seen before, it's PSPACE complete when we have no promise at all on how the gap looks like. So what we show in this context is that the moment you have an inverse polynomial spectral gap, like let's say a lower bound on the spectral gap, the problem immediately becomes PP complete. So phrased another way, the spectral gap provably makes the things and the problem easier in this setting. And you should take this with a pinch of salt, because we are only showing that it goes from something very, very hard, namely PSPACE, to merely something that's very hard, that's PP. Nevertheless, that does not deter us from hoping that it is true in general. So yeah, our next structural property that you could add is a classical description of the ground state. And this is motivated by the following. In condensed matter physics, we can often give polynomial-sized classical descriptions of the ground states from which we can efficiently compute ground state properties. And we want these descriptions to be non-trivial, meaning that you can efficiently compute things based on these descriptions. So an example of this is like a tensor network description of the ground state. Sometimes such a description also inherently has embedded in it a description of a circuit to prepare a ground state, which can be used quantumly. So one really nice question is, do such descriptions always exist for local Hamiltonians? And this is a very physically motivated question for studying ground state properties of interesting Hamiltonians. And it turns out that this is very related to a complexity theoretic question, and it can be phrased in terms of two classes called QMA and QCMA. In short, if the answer to this problem is yes, to this question is yes, then it would imply that these two classes, QMA and QCMA, equal each other. So very briefly for the experts, this is because QMA is the set of problems whose yes instances, whose yes answers can be verified by a quantum verifier with access to a quantum proof or a quantum witness. And QCMA is the same class that of problems that can be verified by a quantum verifier with access to a classical witness. So if the answer to this question were yes, then one can imagine that the prover can, instead of sending a quantum state, can just simply send along a description of the quantum state, which can be taken to be the ground state of a Hamiltonian. And then that would imply that QMA equals QCMA. However, we think that QMA and QCMA are actually different. We have some oracle evidence that they're different. I'm also interested in this problem because it exactly asks this question of what is the set of states with the polynomial circuit complexity and how rich is it, and does that, for example, include the set of, say, ground states of physical Hamiltonians? So with that as motivation, we come to our second main result, which concerns the second structural property of an efficient classical description. So we ask this question of how important is a classical description if there's also a lower bound on the spectral gap. And the answer turns out to be not important, but again, in this regime of inverse exponential precision. So in particular, what we show is that in the same case of inverse polynomial spectral gap, this extra promise that there is some efficient classical description keeps the complexity to be PP. So again, phrased another way, this promise of low circuit complexity of the ground state makes no difference at all if there's already a spectral gap present. And in this light, there's an interesting conjecture or a candidate explanation for this second result. In fact, this conjecture implies the second result, and that's the following. If you have a spectral gap of at least an inverse polynomial, then it implies the existence of some polynomial sized circuit to prepare the low energy state. And I should note that this is a very non-uniform notion of preparing a circuit, which is along the lines of circuit complexity, where you don't care about how hard it is to find the circuit itself, but only care about its existence. So this conjecture implies that most natural Hamiltonians have kind of short circuits to prepare their ground states, because most, say, natural Hamiltonians are either gapped, in which case the spectral gap is constant, or are gapless at critical points, in which case the spectral gap often vanishes inverse polynomially. And this means that this conjecture would imply or kind of explain why variational algorithms seem to be performing well. Because if you kind of search hard enough for some short circuit, you are kind of bound to find it. And moreover, this conjecture would also imply a version of QMA equaling a version of QCMA. And I haven't been precise about what this is, but this is in the presence of a spectral gap. And what we have shown is that the precise versions of these classes in which we are looking at inverse exponential, additive error, these classes coincide. Okay, I'll now briefly talk about the proof ideas. So the PP upper bound proof idea is fairly simple. We prepare a thermal state at some low enough temperature, and the spectral gap, so the lower bound on the spectral gap implies that this low enough temperature state has exponentially good overlap with the ground state. And so you can write this state preparation procedure as in terms of some imaginary time evolution, which you can implement in terms of a Feynman path integral that can be computed in this class PP. And then as for the PP lower bound, we modify the Aronov et al. Construction for the universality of adiabatic quantum computing. Sorry, I missed a citation here. But one extra ingredient that we use is something called the small penalty clock construction, which has several nice features. So this is a technique that allows us to use perturbation theory and keep track of the eigenvalues of the full Hamiltonian and then lower bound the spectral gap of the full Hamiltonian. Okay, so yeah, that brings me to the outlook. So to summarize, we have seen that the spectral gap can make the problem easier. So in the general case, when we have a quantum witness and we're asked to estimate the ground state energy to inverse exponential precision, the problem goes from PSPACE to PP. And when we have a classical witness, meaning that there's an efficient classical description of the ground state or some low enough energy state, then the complexity goes from NP to the PP to PP. And yeah, we have also seen that, this conjecture that a spectral gap could possibly imply the existence of a polynomial sized circuit. And this conjecture would explain why VQE works so well in practice. So there are some open questions, and which may be somewhat more interesting. And so the regime of constant spectral gaps is very interesting. And it would be really nice if we could say something about the non-precise regime. And yeah, it would be also really nice to explore connections to area loss and tensor network representations. So at this point, I'd like to actually take a poll on this conjecture. And so I've flashed this here. And the question is, which way do you lean on the conjecture displayed here? So the options are true, false, undecided, and yeah, maybe not so interesting. Maybe because you are interested in, say, constant spectral gaps or something. So please go to the link here. I'm also just posting this on Slack. Where what you'll see is a window like this, and you can just click on one of the options and submit. So I'll maybe switch over to the results window. I see that Norbert Schuch asks, can you state the conjecture more precisely? Sure. So consider a family of Hamiltonians where you're promised that the spectral gap of this family of Hamiltonians is at least inverse polynomial. And the conjecture is that, so let's consider unique ground states. And the conjecture is that these ground states have polynomial sized circuits starting from say the all zeros product state to prepare them. And yeah, this conjecture is not necessarily claiming that these circuits are efficient to find. So for example, yeah, this could include, for example, NP hard cases where the where the intended target state is just a product state. And so there's like a trivial constant depth circuit to prepare it if you know what state you want to prepare. And what precision in energy? You could ask for inverse polynomial precision in energy or inverse exponential. The way I stated it in the paper is inverse exponential precision, which is obviously a much stronger form of the conjecture. But you could also, you could also weaken the conjecture and then get perhaps hope for it to be more likely to be true. Okay, with that, I can maybe conclude. And I hope everyone's able to see this. So so far I have 8 votes for true, 3 for false, 14 undecided, and 1 not so interesting. Thank you all for voting.
Are you done, Abhinav?
Yeah, I'm done.
Okay, thanks very much for the great talk and also very interesting poll. So we have quite a few questions. I assume you also see the questions, so I'm guessing roundtable would be a better place for the first question because there are already 10 replies. If you want to briefly comment, or shall I? So the first question says, don't the type QMA constructions have a 1 over polynomial gap?
Okay, I haven't read all the replies here, but so what we know is that we know upper bounds on the spectral gap for QMA hard instances of the local Hamiltonian problem, but we do not know lower bounds on the spectral gap. Sometimes what has been studied is the spectral gap of the so-called propagator Hamiltonian, but not the full Hamiltonian.
Okay, so I think we can take at least one more question. So I'm going to the second question. Is this true that QMA is the same as QCMA if the desired property is not the ground state energy but some physical property?
I don't fully understand the question actually. Yeah, maybe we could take it to the round table or follow up on Slack.
For this question, so we have Raz Franco is asking if there is a very good approximation to such a ground state of a polynomially gapped Hamiltonian. Does this also collapse?
Does this also collapse? Meaning, oh, I think the question was in the context of the QMA versus QCMA problem.
Yes.
Yeah, so like, yeah, I don't think there's any serious complexity theoretic, conjecture that we believe would be false if this were true. Yeah, so to rephrase it, in the presence of spectral gaps, yeah, nothing serious, nothing bad would happen if QMA were equal to QCMA.
I'm not sure if we have time for one more question. So yes, but there are questions and the number of replies. So I have to figure out. So again, one question from Norbert is asking, can you state the conjecture more precisely?
Oh yeah,
Precision and
I
energy.
just saw that and tried to answer. Yeah, I think Norbert talks about the accuracy, and yeah, that's really important. I agree. Yeah, I think he also asks whether I have a conjecture whether a gap helps for problems with 1/, poly accuracy. And yeah, that's in fact what the conjecture is about. Like our results, our rigorous results are about the inverse exponential precision case or the precise regime. And the conjecture is for the, the 1/, poly regime.
Okay, I wonder if you can briefly also reply to Barbara's question. She's asking, can you say more about this perturbative technique that you mentioned?
Yes. So actually, I can move on to the appendix.
So we have 1 minute, please.
Sorry. Yeah, okay. So let's consider the typical clock Hamiltonian construction, where we have a bunch of terms that seek to enforce like a good QMA computation. So in like a typical clock construction, we have this output term at the end, which penalizes computations that say no. And the small penalty clock construction is just taking this strength of this term to be kind of small. And we can do that because we are talking about precisely computing these output, these ground state energies. And so we can afford to sometimes even take this inverse exponentially small. And what that allows us is to use perturbation theory or Schrieffer-Wolff to analyze these low energy states whenever this epsilon is much smaller than the spectral gap of the other terms in the Hamiltonian.
I'm guessing it is in the interest of the time to just wrap up here. And for the round table, after the third talk, everybody can join. There's going to be a separate round table discussion for each talk. Yeah. Thanks very much again for the time.
Yeah, thanks all for the questions.